Start recording. Yes. Sweet. Hey, Ashwath, you mind saying something real quick?
Yeah, hello.
Okay, perfect. Yeah, that's good. Thanks.
All right.
Okay. Great. So I guess if everybody's here, everybody can see my screen. We'll go ahead and start. Welcome to 389E class number 2. I guess we're obligated to tell you that since this is being recorded, your consent to being recorded is implicit. So if you don't want to be recorded, then just hop off the voice channel or just mute yourself, and you should be all good. Great. Okay, that being said, today's kind of about logic gates, so let's go ahead and get started. Okay, just a little bit of Administrivia here. Install and setup of 389E Minecraft. That installer is coming out imminently. And for help with installation, I'll be hanging around here on Discord from like 3 to 5 on the office hours channel. And if you need more help, just send me a ping through Discord or send Ashwath a ping through Discord, and we should be available to help you out with installation if necessary. Reason being for that is Project Zero is due on Elms on Monday. There'll be an assignment there, and do send us an email or a ping on Discord if you are not, for whatever reason, on the Elms page. We recently just had Anwar publish it for us, so if there are any problems, let us know, because we have to send him an email, I think, to get that fixed. So we want to get that resolved as soon as possible. And the course website will be updated tonight with today's slides and information for this week. So we will see how that goes. But yes, that's what we've got. We'll talk a little bit more about Project 1 at the end of the class. So that'll be released soon, and then you'll get your conceptual knowledge in today's lecture, kind of some additional information there online, and that'll be due in not next Monday, but on the coming Monday. Yes, okay.
Also, wait. While we're on administrative stuff, I just published the first extra credit quiz on Elms. You should be able to see it. Let me know if you don't. It's going to be due tonight at midnight. And it's a question that if you're here at 11 o'clock, you should be able to answer pretty easily.
Yes, sir. Perfect.
And even if you weren't here at 11 o'clock and you're watching the recording, the answer is Aki couldn't hear anyone.
Perfect. I know we've got one person who says Discord is like disabled where he lives, so I'm gonna go ahead and drop it in the announcements. Great. Thanks, Ashwath. Awesome. Okay. Cool. I guess we'll go ahead and get started then. So inputs and outputs. The gist of it is the basic logic gates that we've covered in 250. They make up all of our circuits. So and or not an XOR. And I'm assuming that most everybody here has already gone through 250, and if not, you're going through 250 right now, and that should be probably what you're covering. Ashwath, is that true? Is that what they're doing right now?
Yeah, they were mainly doing like basic logic stuff last week. I'm not sure this week. I think they probably moved on to circuits and base 2 and stuff like that.
Oh, perfect. Okay, great. So this has already been covered. Awesome. So more advanced gates are just combinations of these 4 gates mentioned above, right? NOR and XNOR, etc. But really what we're going to focus on here is like the abstract concept of gates, because we're going to try to build them in Minecraft. So we want to take note that all of these gates require 2 inputs and produce 1 output, with the NOT gate being the exception because it takes 1 input and produces 1 output. So keeping that in mind, let's think about how logic gates are the most basic constructs of the redstone circuits we'll be building in this class, right? We need to sort of embrace the idea that using the logic gates as a basis, we can build just about any circuit, right? And we'll talk a little bit more about how that's possible a little later. But as you can imagine, since Minecraft kind of lets you work with logic in this way, there are pretty easy ways to represent these logic gates using Minecraft's built-in redstone mechanics. Again, we've got like a little bit of reading there, in case that little bit is unclear. You want some more information on that. We'll talk more about that as well. So how can we take our understanding of logic gates and translate it into redstone? Well, we're going to go step by step, making clear connections with like redstone concepts along the way. So let's take it bit by bit. So first things first, the input for a logic gate, as you know, is composed of one or two values, right? Both of which can either be true or false. Here we've got two, I'm representing this here with two redstone wires, right? A wire with a current that is true and a wire without current would be false. So here we've got two wires, kind of visual representation of this, um, which represent like two false inputs, right? And similarly, when they turn on, you've got two trues coming in to a logic gate. So this is very similar to like when you have a logic gate and you draw two inputs in there, right? So I want you to associate a redstone wire that's on with a value of 1 or true, and a redstone wire that is off with a value of 0 or false. That's kind of what we're trying to get at here. Um, and can we think of outputs in the same way? Yes, we totally can, right? That's kind of what we're getting at here. So when we think of this as a high level abstraction, again, output can be represented by a single redstone wire coming out of our logic gate. If the wire carries current, that means the logic gate returned true. If it does not, it has a state of false, right? So when we put these things together, we kind of get something that looks like this. A way to represent input and output for our logic gates using redstone wires. So in other words, we know certainly that when we're building logic gates in Minecraft, we'll have either one or two redstone wires coming in to this construct here. We're kind of abstracting it right now, and coming out of it, we'll have one redstone wire. Does that make sense? Does anybody have any questions as to why this would be the way that it is?
Is it possible to have two different outputs coming out?
Not in this case, right? Because when we're thinking of logic gates will by default only have one output coming out. When you're building things, obviously it's possible to have two outputs coming out. This if you're not building a logic gate, right? But specifically for logic gates, I want you to think of and, or, not, and XOR. You'll only have one output coming out. Does that answer your question?
Yeah, because
Note
it's
that
more
in
like
a
50.
Oh, got it. Okay, cool.
yeah, note that in a similar vein, most all logic gates will have two inputs. The only one that doesn't is the unary operator, which does not, which will just flip the current that goes in.
Exactly. Cool. So that being said, let's take a look at this little question mark bit that we've got here. Now we're going to take this little abstracted bit and actually figure out, what's in there, right? What are we going to use to represent this chunk right here? And so that moves us on to the basic logic gates. Now, in previous semesters, we kind of covered the basic logic gates and gave you like little truth table for each of them. I'm not going to do that because everybody here probably knows what's going on, but the online resource textbook has like a little review of the logic gates if you so desire. Um, so yeah, let's figure out what goes into this little mystery box here when we want to build a not, and, or an XOR. Obviously, the unary operator not will only have one input, just like Ashwath mentioned. So we've got live demos of these actually in Minecraft. Let's see if this works the first time I'm trying this. Um, so I'm just gonna click through maybe one or two of them. Here we've got so this is the online textbook thing, and you can see the NOT gate is very simple, right? This is just a redstone torch used as an inverter. Here, the red wool signifies input, so we have current coming in here. And whatever comes in here, whether it's on or off, will be inverted because of the way this redstone torch is placed, and the opposite signal will come out here. So in other words, if this wire is on, this will be off. And if this wire is off, this wire will be on. And again, you're welcome to build this yourself and kind of mess around with it and see what happens.
Just to clarify just a little bit more, because I did get a couple questions about this for Project Zero. The reason this works, if you're not familiar with Minecraft as a whole, is the if the wire on the left, the one that's coming out of the red block, if that's turned on, it'll power the grass block on the right, or the dirt block, whatever that's called.
Mhm.
And because that block is powered, the torch on the end of it will be off because the block already has power, and so that torch will shut off, and the current coming out of the torch will reflect the current of the torch, which will be off. And that's the reason the inverter works like that. And same for the opposite current. So if there's no current passed to the grass block, the torch will be on, and the wire coming out of the torch will be on.
Perfect. Thanks, Ashwat. That was helpful. Yeah, it's weird to think about the torch being an inverter as well, especially with the current coming in and the torch turning off. But yeah, perfect way to explain it. Um,
Yeah, it's just slightly confusing because you can't use the torch on its own as an inverter. You need the block there, which is I think what some people were confused about.
Oh, for sure. Yeah, no, definitely. That's one thing. Perfect. Cool. Okay. And the other, okay, so we'll just go through the rest of them. The AND gate as well. It's also, it looks a little strange. It's a little harder to kind of see immediately why this is, the way that it is. Um, but again, it has to do with blocks being powered and the torches reacting to the blocks that they're attached to, right? Here you can see that the input here, the red, both need to be producing a signal that's on in order for this final torch down here to be inverting an off signal, which is a little weird to think about. But basically, I guess the main takeaway here is that only when these two are on, this will produce a signal output. So again, feel free to build these right in Minecraft and mess around with them yourself. And as we move over to ore, I mean, this one should be kind of think about it. This one is the easiest of them all, just because in Minecraft the redstone wire itself is like a kind of a built-in ore gate. And I want to take this opportunity here to explain why these repeaters are here. Um, so repeaters not only act as current extenders in Minecraft, but they also act as diodes, right? And what that means is that when you have current flowing through them in one direction, current will not be allowed to flow back the other direction. In other words, this OR gate, it is what it is, right? If this is powered, then power is going to reach the blue block. If this is powered, power is going to reach the blue block, right? So whether this red one or this red one are powered, power will always reach the blue block. The key here is that let's say you have not an input block here, but maybe some other sensitive circuit on this side, right? You don't want current to come out of this block and flow into here. That's not something you want to happen. So we use diodes here, or these redstone repeaters, to prevent the backflow. By the way, just to clarify, does everybody know what a diode is?
I think you just explained it pretty well.
Oh,
You just
perfect.
you
Okay.
want to prevent the flow of current in a direction that you don't want it.
Perfect. Yep, that's essentially the purpose of the repeaters here, right? So you can never hurt to have too many of these repeaters, just because it'll prevent current from flowing backwards through them, right? So that's why these diodes are, or these, I always call them diodes. These redstone repeaters are placed here.
Also, while we're on the subject of repeaters, they also add delay to a circuit if you right-click them. So we'll encounter that later, but just don't get trigger happy with repeaters because it could really slow down your circuit.
Oh, yes, okay, good point. Cool. And finally, we've got the XOR gate. Just wanted to quickly show that one too. This one's a little weird in terms of an actual demo. This is the one
This
that
one's
I
the
used.
most complicated for sure.
There are a few different ways to build the XOR gate. You'll find that, I mean, the reason I included this in the demo is because you'll find that in Minecraft there are many different ways to build like slightly more complicated gates, like especially XOR. I think there are definitely like a few ways to build XOR, right? And you'll find that these are all created by these like redstone engineers who are desperately trying to moosh these gates into like the most complicated small area possible. I don't know. I guess the reason I use this gate is because it doesn't take up that much vertical space, so it kind of goes with the rest of the gates. But it goes without saying that the difference between this gate, this XOR gate, and maybe one you may find on YouTube is as long as they're functionally the same, you should have no problem implementing whatever you'd like, right? This is just an example on here. This is the one that I memorized and started using. But you're welcome to use whatever you'd like. Again, XOR kind of works in the exact way that you'd expect it to, with current coming out of here, and blue only being on if one of these exclusively are on. Won't take too much time to talk about that since we probably all know what it is.
Also, just a quick note while we're on this complicated circuit. All the circuits and stuff that we're going to recommend you use, like this circuit and the previous, and the ones that we'll get to with like adders and half adders, they're all just going to be like blocks, wires, and torches and repeaters. You can see stuff online that'll like make your life maybe easier with like pistons and stuff, but we can't guarantee that like those will be uh either functionally, if they're functionally equivalent, good for you. You can use it, but otherwise, we can't guarantee that it won't like mess up your circuit because I know pistons like move stuff around and you might run into some issues there.
Then also pistons are kind of laggy and they'll mess up if you're like someone else loads your world and stuff like that.
Yeah, that's an excellent point. I would just go ahead and go on a limb and say don't use pistons at all. I used pistons for like one of my projects, and it caused problems when I like ran the test just because it was slow. Especially when you have a lot of pistons firing at the same time in a world, it just screws stuff up sometimes. And again, the whole problem with like somebody loading your world with the pistons and the release state. So yeah, I would go ahead and just stay away from the pistons when you're building these in particular. Yeah, just for the purpose. So pistons in general, when you're playing Minecraft, they're totally fine to use. It's just that for this class, the way our testing framework works and the way like world sharing works with pistons that are already like extended. I'm not sure if they like addressed that in like a recent bug fix or anything, but don't want to take any chances. Just stay away from the pistons. Great point, Ashwat. Cool. Okay. Again, those websites that I just pulled up are going to be linked on the course website by tonight. So feel free to take a deeper look at them if you want. Right. Okay. So if you've taken 250 already, this is stuff you should already know, right? And again, more stuff on there. And I was what's 250 TA. I feel like I keep saying that a lot. But yes, so you should be good to go in terms of the logic gates. Right. Little nuances to remember. Redstone torch placed correctly will invert current, right? Just like Ashwath mentioned, you have to put that redstone torch on another block, right? You can't just have it placed in the middle of your current. That's not going to do anything. We need it attached to the side of a block so that it'll invert current. Otherwise, it will not perform as you expect it to in terms of inverting current. Secondly, did you want to say something, Ashwat?
I was going to say top of the block works too, but the rest of the current has to be on the same elevation. So like if you want to put wire into a block and then have everything one up, the top of, like putting a torch on top of the block will work there too.
Oh, yes, perfect. Yeah. Second thing is repeaters will extend current and act as diodes. So they're useful to prevent backflow, like in OR gates and things like that. Um, go ahead and use them if you do not want current to flow backwards. Also, there are ways to build these with comparators, but it's not entirely encouraged just because I don't know if we're going to mess with signal strength using our mod or not. And for now, I wouldn't take any chances. Um, but feel free to use them. We will issue a bulletin should they become unusable with our mod setup. So again, feel free to use them. I know there's a quicker XOR gate with comparators, so if that's your cup of tea, go ahead. And we'll let you know when it becomes if and when it becomes impossible to use them. So yes, that's there. Again, we probably won't be covering the functionality of comparators in this class, because we like to keep it vanilla. Right on. Okay. I just want to talk a little bit about logical complements too, on the topic of logic gates. So occasionally we have a gate or circuit that produces the exact opposite of what we want. And in this case, all we have to do is use the logical complement of whatever gate or circuit you've got, right? So you might notice when we have the NAND gate, right? You just draw the NAND symbol with a little circle in front. Oh, sorry, the AND symbol with a little circle in front of it, right? And that's what I mean by using dot notation. Um, so you've got an AND gate and you want the exact opposite of it. So instead of slapping an extra NOT gate in front of it, you would just put the little circle in front of it, right? And I mainly covered that just so we talk a little bit about NAND and NOR, just because those gates are used sometimes, frequently, and NAND is sort of important. Um, so that's just a quick way to represent the NAND gate and the NOR gate. Again, we've got some more literature online to take a look at if you want to read more into that. Right, this is an exercise. We usually just do this in class, but we'll give you like a minute or two. See if you can construct an XOR gate using only OR gates, AND gates, and NOT gates. So I'll give you like a few minutes to just kind of try this on like a piece of paper if you've got one in front of you. Or if you're watching the webcast, just like, I don't know, pause it for a little bit and unpause it when you're done. Um, but yeah, while you guys are kind of giving this a try, I want to emphasize that you should try to be as efficient as possible, right? In real life, circuits are made by hand, and every piece has a cost. Here, the only real cost is probably getting carpal tunnel from building too many of these things in Minecraft, but still a very real problem. Again, more gates equals more build time, so I guess the one benefit here is that you kind of learn to think efficiently. So we'll go ahead and give you like a minute or so for this kind of. Well, also it occurred to me that we usually do this segment on like the board.
Yeah, I assume you have the solution on the next slide.
I may or may not.
Oh, okay.
Let's see, it might be somewhere near. Let's see.
I mean, the solution's online, so
Yes.
we can always just Google it.
Let's see. Yeah, I might as well. I think I can pull it up from then. Let's see. I'll just. I can try and pull it up from the. There we go. I think we had from last year's lecture. There we go.
I feel like last year we ended up drawing it on the board, right?
I think so. Yeah. Oh, you know what? You're right. Here I've got one from Wikipedia that's got and not. There are a few ways to do it. There we go. I found it. All right, cool. So if everybody's kind of given that a try, I'm gonna go ahead and I think this is a pretty good one. The diagram's a little odd, but I tried to pick one with the visual representation here. And you can see it's doable with and or not and again here when you have and not, you can condense that into a NAND gate. I just wanted to find an example here which didn't have the little dot circles. So yeah, this is kind of what you're looking at, right? And here we wanted to emphasize one thing with this exercise. So again, I mean, if you're watching the webcast, this is one of your solutions here. By the way, this is not the only solution. There are other ways to do this. This is just a solution. We consider it to be pretty efficient. Okay, cool. I'm gonna leave that on there for like a second. Okay, I'm gonna move it off to the side now. Close that. Why is this so important, right? Some gates can be built using other gates. That's kind of what we want to emphasize here, right? And that kind of opens the door for us because we want to ask some more questions about building gates with other gates. Fundamentally, there are a lot of things we can do in that regard. And that kind of takes us over to applications in computing, right? So that's like another aspect of this class. We're going to talk about not only the components that you're building, um, but how exactly they kind of pertain to the computing world and a little bit of background knowledge and relevance for you in that sense. So let's talk about the NAND gate, right? And that is just the AND gate with a not in front of it, right? So you're just taking an AND gate and placing an inverter at the end of it, and we're calling that the NAND gate. They actually end up being the most commonly found gates in computers. A small example of this would be if you've ever heard the term NAND flash, right? Um, that is because the flash memory itself is just consisting all of NAND gates. So the question we're going to address here is why that is. Why the NAND gate is the most commonly found gate in computers. And one of the reasons is that the NAND gate is functionally complete, right? And we'll talk a little bit about functionally complete in a moment here, but I want to address that the NOR gate is also functionally complete as well. So let's talk about that, right? Uh, Here, that basically means you can build every other gate using the NAND gate, right? For example, here is the NOT gate. That can be easily represented using NAND, right? Feel free to kind of work through the truth table in your head. See that if you put the same input into both sides of the NAND gate, you get the inverted signal coming out. Similarly, if you pull some gymnastics here with the NAND gate, you can also figure out the AND gate pretty easily. Just by feeding these two inputs into an inverter and then throwing them into another NAND gate, right? So those are relatively simple examples. And it turns out you can build the other gates as well. So here's an OR gate, right? Slightly more complex here. You notice it takes 3 NAND gates to produce an OR gate. And finally, we move over to XOR, which is the most complicated, but you can see very simply that it's still doable with a NAND gate. And we want to specify here that the reason this NAND gate is so special is because in all 4 of these designs here, 1, 2, 3, 4, we are only exclusively using NAND gates, right? So in other words, we only had to produce one type of gate, and we had to maybe use them 1 or 2 times, in this case 4 times. We only had to produce one type of gate, and using that one type of gate, we can create all these different logic gates. So that's the kind of key there, right? So if a gate is functionally complete, all other gates can be constructed using it. And in a common circuit manufacturing and fabrication process called CMOS, the NAND gate is smaller and faster to make than a NOR gate, right? And that kind of was a positive feedback loop. The gate was very easy to produce, so a lot of people made a lot of these gates, and now they're just, because of this overall pattern that's kind of been sitting around in the industry for a while. It's the cheapest to buy NAND gates, right? To the point where to build maybe a simple basic circuit, manufacturers do not want to buy, oh, I want one NAND gate and I want like two OR gates and an XOR gate. No, they'll be like, here, I'll just buy 50 NAND gates from you, and that'll be cheap, right? Manufacturing likes to happen in bulk. And in this case, buying a crap ton of NAND gates basically means that you'll be able to build whatever you want. So that's the kind of key there, and that's why NAND gates are so big in computing these days. So thanks to already set industry precedents, right? The initial ease to manufacture them, NAND gates are, basically the pick over NOR gates, because again, theoretically, you could do the same thing with NOR gates and use it as a universal gate to build all the other gates. But here, most manufacturers will just say, okay, I want to build some logic circuits, so let me just buy a ton of NAND gates and put them all together, and that should totally work out. Um, so yes, there's more, I guess, online reading related to this if you are interested. And now applications in Minecraft, because that's the other half of this class. Why is this big for us? Well, we're gonna prove something here, if you will. I didn't do so well in 250, but if you'll humor me, we've got a little bit of a proof of sorts. Um, we are able to create a NAND gate in Minecraft. And you should read that as we are able to create a fully functional computer in Minecraft, right? Knowing that we can create a NAND gate in Minecraft, and also knowing that a NAND gate can be used to build every other gate, we have therefore proven that we can build a computer within Minecraft. Reason being, computers themselves are composed only of logic gates, right? That's what circuits are made of. And if we know for a fact that we can build every single circuit um, within like a system within Minecraft, uh, then we can build a fully functional computer, right? And I want you to think of computer not in the physical sense. That's kind of we're trying to distance ourselves from that when we talk about digital logic. I want you to think of particularly like the computational sense, right? We can build a system where we are able to provide input and it will compute using that input and produce output, right? Um, so in that sense, we can say Minecraft is there's another term here that's worth looking into. It's called Turing complete. And similarly, as a little bit of a fun fact, Minecraft has all these systems in place to make it Turing complete, but so does Microsoft PowerPoint, right? So there's like this neat project online where somebody's actually taken PowerPoint and made this elaborate, weird little punch card system out of PowerPoint slides. So you can program a .pptx file to do very basic computing tasks. So that's what I kind of mean by we can build a fully functional computer. I don't want you to think of a physical computer. We want to think of like a construct that can perform these computations for us, right? So there's a little tidbit there. Does this mean we will build everything using NAND gates in Minecraft? No, absolutely not. That's completely ridiculous. That just means carpal tunnel. It'll be horrible and terrible to look at. Not very cool, right? What we're realistically looking at, it's even though in real life it may be advantageous to build a lot of these circuits out of solely NAND gates, we have to consider the subtle yet key differences between Minecraft and real life. Yeah, actually, that just makes me sound like a weird Minecraft person. Um, but again, take note, right? Just because NAND gates are a very easy way to put things together in real life, doesn't mean that it's the most efficient way. The most efficient way to build these circuits within Minecraft. So again, Minecraft digital logic is a great analog to digital logic in real life, but take note of the key subtle differences that we've got here between the two. Right, efficient circuit design. And this is kind of the building off of the little XOR exercise that we did. But let's recall that when we're building these circuits, so we kind of know that in Minecraft we can build all these logic gates, right? That's good. You have the power to do that. Now let's talk a little bit about efficiency. We want to create the circuits that, in a given input, produce output that we desire. But not only that, we want to do this with as few components as possible, right? So when discussing Boolean logic, we should think about the logic rules that come along with them. And you'll see that we'll delve a little bit more into 250 here when we relate digital logic circuits to Boolean predicates, right? So in other words, we can use logic rules to perform simplifications on our circuits when needed. And I've linked Telly's logic laws, the equivalencies here on the slide. If you do want to take a look at, or you can just Google CMSC 250 equivalencies sheet or discrete math logical equivalencies, and you should get it. So I'll just actually let me go ahead and I'll copy the link address, and I'll go ahead and throw it in the chat for lecture questions. Oh, I've seen questions. So, oh man, okay, I haven't even seen these. My bad.
Oh shit, I forgot to look too.
You're good. Yeah, no Doom. Again, it's because of the 20 tick thing. Yes, Computercraft is able to emulate a literal computer. Again, people sometimes cheat around and use the Java built in on Minecraft to run some of this stuff in the background. So I like to think of the real examples as the ones based entirely in vanilla Minecraft. Exactly. Yeah. So they kind of, it's almost like bridging to a virtual machine when you do that, right? So I feel like it's kind of cheating there because in that case, you're not building a computer in Minecraft. You're really just building a computer in Java. Um, Again, we could be thinking of different mods, so forgive me if I'm wrong, but that's kind of my stance on the computers within Minecraft mods, because anybody can build a computer in Java. The real key is building a computer in Minecraft. So again, if you consider command blocks legit, yeah, no, that's the thing. Command blocks, again, I feel like they're leveraging Java to build something, right? But I mean, they're totally cool creations at the end of the day. Very neat stuff. Command blocks get pretty crazy these days. Again, we'll be staying away from command blocks in this class, just because they kind of, yeah, exactly. They undermine what we're trying to do here by using just the constructs of Minecraft to build like a computing circuit.
I mean, pretty much our final project could be accomplished with one command block, so that they're pretty not legit in that sense.
It's true. So I've posted the link here to this logic laws in case you want to follow along. Take a look at this. But moving along here, when you go ahead and give this a try, suppose you're given the following circuit, right? And I want you to think about how you'd go about simplifying this. Um, so again, the first thing you should probably do when given a circuit like this is think back to 250 and decide, okay, we're going to represent this using Boolean logic. Well, I sure hope that's right. And you can see here that we've kind of distilled it down to this logical predicate. And now when you take a look at it and you consider the equivalency laws, I'm just going to give you like a minute or two to kind of think about, okay, what could be one of the equivalency laws that we could use here? I think it becomes a lot more easy to see if you flip the order of A and B in the first one. But after giving you a little bit of a second here, we can kind of see that if we use the logical equivalencies, again, if you're watching the webcast, you feel free to pause it and wait until you get it and then move on. I'm just going to go over and hop to the next slide. No qualms with that, right? All right. This is what we get, right? We use the distributive law to provide the following. You can see here that it's a pretty huge change in terms of building it in Minecraft, right? Over here on the left, we had to build 2 AND gates and 1 OR gate. Now we're just down to 1 AND gate and 1 OR gate. And the result here is that we're producing something that's functionally equivalent to what we had here. But here, we produced it using a lot less effort than we did here, right? And that's one of the key things to keep in mind when you're designing and building circuits in Minecraft, and you perhaps come up with an idea, okay, I can use these logic gates here to produce the output that we want. Just think about it for like a second, right? Draw it all out or write it out as a Boolean predicate and think, hey, can I simplify this, make this a lot easier for me? Because an extra minute spent just figuring out this Boolean logic could be, like 10, 15 minutes of just you building extraneous surplus logic gates within Minecraft. So again, just something to consider as you move through this. So key takeaways here, right? Knowing the basics of Boolean logic opens the door for us to make much more advanced circuits, right? And understanding functional completeness in that sense gives us the theoretical knowledge to know just how computers can be created in Minecraft. In other words, Minecraft is functionally complete. We know how to make some of these logic gates, and therefore we know how to make all of these logic gates. Therefore, we can build an entire computer in Minecraft. So again, by extension, it's just knowing that concept, figuring that out, knowing that because you can make a NAND gate, you can make a computer in Minecraft. That's also another key thing to consider. And of course, Boolean logic rules are essential to designing circuits in the most efficient way possible. In the real world, this saves us time, money, and materials. In Minecraft, it really just saves us from wrist computer diseases, but also time. So again, something to keep in mind. It's good practice to sort of be able to distill these down, and again, goes really hand in hand with 250 exercises about simplifying logical predicates. So, hopefully most of us have had some practice with that already. What if you already have carpal tunnel? Excellent question. Can't help you there, but try not to make it worse. Because I do. That is not a problem. I hope you were doing well. Truly.
I mean,
Yes.
jokes aside, I mean the project in this class shouldn't take too long, so I feel like carpal tunnel shouldn't be a massive issue.
Yeah, absolutely. To replace 245 with this class, we are working on 244 right now, actually, if that's still digital logic design. But yeah, it should be fine. Also, if anybody needs any accommodations at all whatsoever, we're totally open to that, right? So go ahead and send us an email or a message, and we'll go ahead and escalate that. Project Zero is on the course website, Brian, and we will go ahead and get that on Elms as soon as possible. I just saw yesterday that Anwar had given us Elms publish access. So
I hope that he gives us submit server access soon as well, so we can
yeah.
actually get the submit command working.
I think we're still waiting on that. I've been sending him emails, but I guess I can assume he's been busy. We'll get there though. So right now we're gonna go via Elms. I think let's see, do I have any more slides? Yes, okay, just one that said project one. But we can answer questions in the chat before that. If you'd like. We're on the course website. So you see on the course, actually I can throw it up right now. Why don't I do that? Here. Okay, I had it open, I think. Oh no, actually you're looking at this screen. Okay, check it out. So you guys can still see this, right? Over here on the course website, if you want to find the project, just go to week 1, right? And this will be the project, Tutorial Island. You go ahead and click the link that says PDF, and it'll open up the LaTeX document that Ashwath has put together describing project 1 and the functionality that needs to be implemented here. So again, this is assuming that you've installed Minecraft already, given the installation instructions on the website. So does that help, Brian? You good to go there? All right, I can go ahead and throw. Yes, okay, cool. I'm gonna go ahead and throw the link as well into the chat, because that's where we'll be putting everything for now. We're kind of sidestepping around the limitations that the CS department has put on us for now, just with material publishing and stuff for the course. But if you bear with us, we'll get the submit server up. Elms will be populated. It's just been a little slower than usual, probably because of the massive volume of courses going online. So we will try to make it as painless and easy for everybody right now. Ashwath, did you want to talk about Project One? I don't mean to take away time from you here.
Oh yeah, no worries. Yeah, Project One, it'll come out either tonight or tomorrow. And it'll just be essentially what's covered in this lecture, but you're gonna do it in Minecraft. So just as a brief overview of what you're gonna be doing, it's gonna be you're gonna have 3 inputs designated as A inputs and 3 inputs designated as B inputs, and essentially you're just gonna make 3-bit logic gates. So essentially, it's just gonna be like 3 AND gates, 3 OR gates, 3 XOR gates, and 3 NOT gates. So that's all it is for this project, just to get you some practice with the building the gates, and obviously these will be used going forward. And it's like the exact way that you're going to make it for this project is going to be used in what's called the ALU, which will be completed by Project 4.
Perfect. Yep. So again, I think we've got videos on that actually, so maybe put that together and throw it on the course website as well. So stay tuned for that. All of that should be coming out, latest by the end of this weekend. Might have to spend some time messing around with Elms as well. The goal is to have Elms and the course website mirror each other, so you can either check the course website or Elms to get all the information that you want. We will let you know when that is happening. But I'd say for now, most up-to-date resource, just go ahead and check the course website, and everything should be organized there in one little chunk. I think what we're gonna do for I guess like the coming weeks is we're gonna keep stuff on the course website, but also on Elms, we're gonna put them in little modules so that each week you know exactly what to do just by clicking like the week X module. So we're experimenting with that. We'll see how that goes, and that should hopefully be okay. Right. Cool. That's all we've got for the. That's all I've got for the presentation. Also, did you want to add anything?
Nope. I guess we can just take questions if everyone has.
Sweet. Yeah, sure. Feel free to hop in here with questions. Also, as a side thing, feel free to like message in the like the general chat as well. Would anybody be interested in coming from 3 to 5 today, for me to help you with install? Or are we all good in the way of installation?
I might come by because I'm still a little like confused on like how to like properly integrate things, but yeah. So
Yeah.
maybe I'll figure it out myself before then.
Yeah, no problem. Okay, cool. So I'll be hanging around there either way then. So that should be fine. I guess just installing it and making sure that it works. I know our submit command is having some trouble right now just because the submit server is I don't think we've even got one set up, but hopefully we're gonna get somebody on that. Yes. Cool. So feel free to ask questions. I'm gonna go and stop the recording now. For those of you who are just here to hang around, thanks for coming. Will you be? Yes. Yeah, no problem. So yeah, I'll stop the recording.